Hello and welcome to the next video on topic 5 on sampling distributions. Here in part 5 we'll be talking about the behavior of the sample means, and we'll do some examples that try to illustrate some of the important ideas from part 4's video. So if you have not yet seen the video for part 4, I highly recommend you go back and look at that and pay particular attention to the information given about the central limit theorem. So assuming you've seen part 4's video, let's start with an example about the salary of city workers. So suppose the annual salary of city workers in a certain city has a mean of $52,000 and a standard deviation of sigma equals $4,000. First question, what is the probability that a randomly chosen worker's salary is more than $53,000? So here we're looking at one of the workers from the entire population, randomly choosing his or her salary and seeing how likely is it that their salary is greater than $53,000. Now, notice that in order to do any kind of probability calculations, we need a probability model. The one we've been talking about a lot is the normal curve. And unfortunately, we don't know for sure whether or not the population data are normally distributed. In fact, salary data is often skewed, and therefore it's not normally distributed. And so we cannot use a normal distribution calculation here like we would normally assume we could. In fact, we can't assume it because we don't know enough about the population's distribution. So for this question, we don't have enough information. If we were, on the other hand, told the population data were normally distributed, then we could proceed. Let's take the same scenario, and now let's ask a different question. What is the probability that the mean salary of a random sample of size 15 is more than $53,000? Now, hopefully you see the difference between this question and the one on the previous slide. The previous slide asked about a particular worker's salary drawn from the population. This is different. It's asking about a sample. So basically what we have is a sample of size 15 that's been chosen from the population, and we want to find out how likely is it that the mean of that sample is more than $53,000. So we're not just looking at one salary or one worker's salary, we're looking at a mean. So we have a completely different distribution to look at here. And in the last video, we talked about this distribution and called it the sampling distribution of sample means. The problem here is that a sample of size 15 is not large enough to invoke the central limit theorem. Recall from part 4's video, the central limit theorem said that if your sample size was at least 30 or more, then the sampling distribution of sample means takes a normal shape. Without that knowledge, we can't do any calculations. And so because we don't have a sample size that's large enough, this is below 30, we still don't have enough information to answer this question. So the purpose of these first two questions are to show you the importance of knowing that your data or that your distribution is normally distributed, that it has a normal shape. Unless you know that, either by looking at the data set and histogram, or by using something like the central limit theorem, or some other criteria that we talked about when we talked about sample proportions, then you're stuck. So keep that in mind as you work with real data. The distribution is important and you should be checking it to make sure you know what that distribution looks like. If we take that same scenario though, and then say, what's the probability that the mean salary of a random sample of size 50 is more than 53,000? So almost everything's the same. The only thing that's changed here is the sample size is now 30 or more. Once we have that, and a sample size that's 30 or more, then we can invoke the central limit theorem, which once again says that the sampling distribution of sample means will have a normal shape if the sample size is 30 or more. So since we know that the sampling distribution of sample means is normally distributed, we can then go ahead and talk about the mean and the standard deviation of that distribution. The mean of that distribution, the mean of the sample means, as we saw in part 4, is the actual mean of the population, and that's already given to us as $52,000. The standard deviation of the sample means, sometimes called the standard error, can be found by taking the population's standard deviation and dividing by the square root of the sample size. So because we have both of these numbers here, we can then compute this to be 565.6854. At this point, we have a couple of choices. As we've seen in previous videos, we can compute the z-score for $53,000 and see how many standard deviations that is above 52,000. And then using a standard normal curve, either tables or technology, we could compute the probability of that z-score being at least that high. On the other hand, because we have technology such as StatCrunch, we can also just put the mean of that sampling distribution and the standard error of that sampling distribution into the software and ask it to compute the probability that a sample of size 50 or more will have a mean of 53,000 or more. And it turns out that the probability of that happening is 0.0385. So in other words, if you took many samples of size 50, then only about 3.85% of them can be expected to have a mean of 53,000 or more. And so it's very unlikely that if you took a sample size of 50 or more, that the mean of salaries that you calculate will be higher than the one that you've gotten here. So that's our first example. It also serves to illustrate the importance of looking at the distribution before you do any calculations. Now let's go ahead and take a look at another somewhat related example, but now let's look at MBA salaries. So suppose Business Weekly has conducted a survey of graduates from 30 top MBA programs in the country. And on the basis of the survey, we'll assume the mean annual salary for graduates 10 years after graduation is $110,000. We'll also assume the standard deviation is $30,000. Furthermore, we'll assume the population data are normally distributed. Suppose you take a simple random sample of 64 graduates. Two questions to answer. A, what's the probability that a single randomly selected salary has a mean value between $120,500 and $125,000? Find the probability that a random sample of size n equals 64 has a mean value between $120,500 and $125,000. So notice that the numbers look very similar, but the questions are asking about two different distributions. One is about the population distribution up here in part A. The other one is about the sampling distribution down here. Also, part A is slightly misworded. It should just say, find the probability that a single randomly selected salary is somewhere between these two numbers. We don't need mean here. That would only apply if we had a sample. So let's strike this out here as we think about this question. Okay, so let's tackle part A first. Here's the basic information that is given to us. These are all parameters. Excuse me, well, two of these three things are parameters. This is the parameter for the population, it's the mean, and this is the parameter for the standard deviation of the population, which is 30,000. And this is our sample size. Right? Part A says find the probability that a single randomly selected salary is between these two numbers here. Again, let's ignore the mean here as it's a typo. So here what we want to do is we want to look at the distribution of the population itself. If you go back and look at the wording of the problem, we are told that we can assume that the population is normally distributed. So here is a representation of that normal distribution. Now, once we know that information, we can put our basic parameters into StatCrunch So we can input the mean of 110,000 and the standard deviation of 30,000 and ask it to compute the probability that a randomly selected salary will be somewhere between 120,500 and 125,000. It turns out that's 0.0546. And that's represented by this shaded area under the normal curve. So roughly 5.5% of all salaries 10 years after graduation will be between $120,500 and $125,000. Keep in mind, this could only be done because we were told that the population data is normally distributed. So now let's take a look at the second question. Part B says, find the probability that a random sample of size n equals 64 has a mean value between $120,500 and $125,000. Now, the wording here is correct because we're trying to figure out how likely it is that if you had a sample size of n equals 64, the mean of that sample is between these two numbers. So this is a correctly worded problem. But notice that up here, we're given the parameters about the population. So we have a little bit of work to do. We need to look at the distribution of the means. And first of all, we need to be able to determine whether or not it's normal. Well, that was pretty easy. Because we know the sample size is n equals 64, then the central limit theorem says that in this situation, because n is 30 or more, then the sampling distribution of sample means is indeed normally shaped. Second, what is the mean and the standard deviation of the sample means? In other words, on this new distribution that looks at all of the different samples we could take, what's the mean and standard deviation? And again, we draw on what we learned in in part 4's video. We know that the mean of the sampling distribution is the same thing as the population mean, or $110,000. We also know then that the standard deviation of the sample distribution of sample means is given by this expression. So we can go ahead and compute that pretty easily with a calculator, and we get 3,750. So our results then from StatCrunch look like this. When we go into StatCrunch and we put in the information for the sampling distribution of sample means, the mean is 110,000. The standard deviation, which we in this case call the standard error, is 3,750. And then we say find the probability that a sample of size 64 will have a sample mean between these two numbers. And this number, this result, is much smaller than the one we saw before. In fact, you can see that the shaded region is way out over here on the tail. Remember, this distribution is different than the original one that we did in the previous slide. The previous distribution told us about, let's go back here real quick, the previous distribution told us about the population of individual selected salaries. This new distribution that we're looking at is related to samples that we take from the population. And so what we're seeing here is that it is highly unlikely. The probability is 0.0025. So that is, what, 2 or 0.3%. And what's happening here is because the sample sizes are 64, those means of those samples of that size are much more likely to be toward the population mean. Most of them are going to be over here. And so it's going to be very difficult to get a sample that has a mean that's out here on the edge. Another way to think about this would be to think about what these two numbers here represent in terms of z-scores on the sampling distribution. These would represent, so 120,500, a sample mean here, is 2.8 standard deviations away from the mean of 110,000. And $125,000 is a whole whopping 4 standard deviations above that mean. So we're talking about z-scores that are way over here on the tail. And we know because of the shape of the normal curve that the area between those two z-scores is going to be incredibly small. And so essentially, practically speaking, all this is telling us then is that there are very, very few sample means that are going to be that far out on the tail over here. Most of them are going to be bunched in here because the sample size is relatively large. So that sort of wraps up topic 5 videos. Hopefully those were useful in helping you to tackle some of the ideas that we've been discussing and also to complete some of the problems you'll see for homework. I hope the video has been helpful, and we'll see you later for topic 6 videos.